We made it. So this is the last video for the review unit, which is just a review of graphing. So if you've taken physics recently, or I don't know if you actually did computer generated graphs in Chem 50 or not, but this is just kind of potentially a reminder of how to generate a graph and also how to interpret a graph. So a graph is a visual representation of an equation. So an equation is going to describe a relationship between two variables, and the graph allows you to picture this relationship. When you're graphing, you want to make sure that you include all the elements, which is a title, right? The title should be clearly state the purpose of the graph and include the independent and dependent variables. The independent and dependent variables are your axes, right? So the labels on your axes, I guess I should say. So the labels on your axes should have the name of the variable and the unit. And the independent variable always goes on your x-axis. Your independent variable is your variable that you can control. So for example, I'm trying to think of like an easy example to explain. All I can think of is physics right now. But if you took a ball and you were dropping it from a height, and then you were looking to see how high the bounce would go, you're controlling the drop height, and then the bounce is the dependent variable. So it depends upon how high you're dropping the ball from. So the independent variable always goes on your x-axis, it's the one that you control, and your dependent variable is your y-axis. You want to make sure you choose a scale carefully. Now, as long as you're doing this computer generated, it does that for you, but you want to make your graph as large as possible if you're doing them by hand. Each point should be plotted as a dark dot. Again, the computer does this for you. And then you want to make sure you understand what a line of best fit means, which on a computer is the trend line. And what it is that you're going to draw a line that best fits the data. So if we have a linear relationship, your data should be increasing proportionally, right? So if you look at this graph down here, we've got this point here at 0, 0, and then you can see that the graph goes up in a straight line. So looking at this, I cannot draw a freehand line, but I've realized that this video isn't capturing my mouse. But what it is that the data is following a line versus a curve, versus versus some other shape. And so if your graph is following that trend, then you can draw a line of best fit, which is a line that passes through as many points as you can and keeps the rest of the points sort of equidistant. So it's just kind of picking the middle, and your computer will call it a trend line. You're not going to be connecting the dots. So you might know this is really great data, but if I didn't have such great data, if I had a data point that was up here, you definitely cannot use that in any calculation because it's off your trend line. Okay, so what are we going to do with this? Well, we can have mathematical equations to represent our data. Our y variable is representing our dependent variable, and that's going to go on the y-axis, obviously, which is the vertical. So in this example, we've got mass, and then you're going to have a slope of a line. So the slope is the constant of variation. So it's the amount that you are rising and running across this graph. The x will be your independent variable, which in this case is volume. And then b will be the y-intercept. Now, we're going to have a lot of data where the y-intercept is going to be 0, right? So for example, this one, it's the relationship of mass and volume for water. So again, my title included my independent and my dependent variable, and it gave some more details. So this is the relationship of mass and water for volume. So different masses of water occupy different volumes, or the way that this graph is done, different volumes have different masses for water. And for this graph, it goes through 0, 0, because if you had no water, it would have no mass. So we would call this a direct linear relationship because it goes through 0, 0, which makes the y-intercept, or the b, 0, which means you would just have y equals mx. Now, what we're going to spend a little bit of time here now doing is calculating and interpreting the slope. So the slope of a line is the rise over the run, or the change in the y values over the change in the x values. When you're finding the slope of a line, you're using the line of best fit, which means you can only use a data point if your graph goes through a data point. Otherwise, you're looking for where your axes, so these minor grid lines, have a cross with your data trend line. So for example, if you look here, like that would be a pretty great point to use on your slope, because it's a point that your graph goes through, and it's easy to tell its coordinates. So the x value here is 40 and the y value there is also 40. Now this graph has excellent data. Whoever collected this lab data was a genius, because you could also pretty much use any data point. But for me, I don't know what these data points are. So even though I know I can use a data point, I don't know what they are. So I'm still going to use 40/40. Now you look here, I could also use 20/20, and then I'm also going to use 0/0. So if I was calculating the slope, it would be the rise, which is 40 up, or the change in y values. So I'm going to use the point 40 minus that origin, 0, over my x value of 40 minus that origin of 0. And I end up with a slope of 1.00, because I'm allowed to go to 2 sig figs. Okay, but what does this slope represent? Well, it's the rise, which is measured in grams, over the run, which is measured in milliliters, which means my rate of change is 1.00 grams per milliliter. Now, if you've taken a bunch of chemistry, you might remember that this is how you calculate density. Density is the grams per milliliter of a substance. So if I was to then write this equation using the slope and appropriate variables, I know the equation is y equals mx, but my y is representing mass, so I'm going to use the letter m for y, and that's what I mean by appropriate variables. Then I'm going to put the 1.00 in for my slope, and then the x is representing volume, which I'm obviously going to use a v. So my equation is m equals 1.00 v, which means that there is, now I'm going to type because I know that my printing can just be so messy sometimes using this tablet. So the relationship is, there is a direct linear relationship between mass and volume of water at a rate of 1.00 grams per milliliter. Okay, and this is us interpreting data, and we're going to be doing this in the lab, and we're going to be doing this in another question, so this will become more rote for you. Plus, if you take physics courses, you've already done this. All right, so now I've got another computer-generated graph for you. This one is the effect of time on the temperature of a water bath. Notice how this title wasn't just the effect of time on temperature. It'd be like, what, air? Right? Like, what are we talking about here? Where as soon as I put the effect of time on the temperature of a water bath, I'm realizing that that means that I have a body of water and I must be heating it. Because what's happening? Well, if I look at the type of relationship displayed in this graph, it is a direct linear relationship, right? Because you can see that my data points are going up in a straight line from 0, 0. So my next job is to find the slope of this line. Again, it's going through 0, 0, so I'm going to use that as one of my data points. And then I have to find somewhere else that my graph goes through either a data point perfectly or somewhere that I can find the coordinates of. So when I look at this one, I'm going to look for a really good data point. Where's a good one? I was almost thinking that one there, but it's a bit too low. Oh, that's a pretty good one. Here, I realize you guys can't see my mouse. I think I'm going to pick this one here. I feel like that one is pretty great. Now we don't have our data to go off of, unfortunately. So I'm just going to go with sig figs based on reading this graph. So I'm going to say that this point here is, now what's my scale? So 2.1, 2, 3, 4, 5. So there's 5 grid lines to get to 4. So 2 divided by 5 is 0.4. So every single grid line is worth 0.4. So 2.4, 2.8, 3.2, 3.6, and 4. So I'm going to say that this is 3.60. It's right on that point. And then my y-axis, it's 1, 2, 3, 4, 5 grid lines to get 5 degrees. So this is going to be 10, 11, 12, 13, 14. And again, I'm going to say, because I picked exactly on the line, I'm going to go 14.0. So I'm dealing with 3 sig figs here. So now I'm going to plug this in, and I'm going to say that it's 14.0 minus 0 over my 3.60 minus 0. And then I'm going to plug that into my calculator. Somewhere. 14 divided by 3.6 is 3.89. Then we want to determine what the slope represents. So my y-axis was my temperature in degrees Celsius. My x-axis was my time in minutes. So my slope is 3.89 degrees Celsius per minute. It's the rate of change, of temp change per minute. So my water bath is rising 3.89 degrees Celsius per minute. What would the equation be? Well, again, it's going through 0, 0, so I'm going to use y equals mx. My y is representing temp, so I'm going to use a t. My x is representing time, so I'm going to use a little t, right? Or you can use an m for minutes, whatever it is, you just have to define it. So I'm going to say that temperature is equal to 3.89 times time. And then if I was to describe this relationship in words, again, I'm going to type. There is a direct linear relationship between temperature of a water bath and time at a rate of 3.89 degrees Celsius per minute. So hopefully this is starting to feel a little bit repetitive, and you'll understand that every linear graph we sort of describe the same way. The variables will change, the scenarios will change, but slope, how we find it is the same, how we interpret slope is the same, and then how we write our relationship in words is pretty much the same. Sorry, my computer has a glitch. I have to hit enter for it to all show up. One thing that I should mention before we move on to the last example is that you'll notice up here that the equation was already on the chart. So this equation is computer generated. They are better than we are. They are computers. And so they knew that this line of best fit went exactly through X data points. And so instead of having human error, which is estimating data points, it does it very precisely. Now it got 3.902. We got 3.89. It's not bad. I do want some element of humanism in interpreting graphs. So, I'm letting you computer generate these. You can put the equation on the graph, but I want to see that you can calculate the slope, right? You understand what slope means. So for this one, we are off by, not a lot, like 0.03 maybe, or even less. I don't know, my brain's not working that quick today. And then if you look back at this one, we calculated the slope to be 1.00. They calculated it to be 0.9847. So not bad in the grand scheme of things, considering we're estimating a point. So the last thing that we're going to do in this video is make sure that you can not just interpret graphs, but you can also draw graphs. So I'm going to show you how to computer generate a graph If you already know how to do this, you could probably just not watch the last part of this video. If you're going to be using Google Sheets, there's a video in the lab you could watch instead. So the instructor Ellie uses Google Sheets, so she talks you through how to use that. But I'm going to use Excel. So what we're going to do is we are going to draw this data where two chemistry students were measuring the mass of a liquid at different volumes, and they predicted that there would be a linear relationship. So you'll notice they say here that they are measuring the mass. That makes that the Y value, or your output. And they're measuring the mass at different volumes. So the volumes is going to be your input. So the first thing you want to make sure is that your chart is set up with your X values, and then your Y values, your outputs, or the things that are results of. And when you look at this data, you can kind of tell these were going to be my inputs for my volume because it's 0, 5, 10, 15. It's nice regular intervals. Whereas on the right-hand side, this is my output. These are my measured data in my lab. So I've already done the first part where I took the data and I put it into Excel, just so you didn't have to watch me type that. And the one thing I wanted to show you is that when I originally put this data in, because all the last digits were all zeros, they only went to one decimal place. Or if I had put one of them as like 12.25, it would have put it down as, sorry, just make sure that's showing on your screen. They would have put it down as like one of the numbers is 12.2, but what we want to show is precision. So in this second column here, in my B column, these were all measured to 2 decimal places, whereas my A column was probably read off of a beaker, and so it was read to the nearest tenth. So to set my B column to 2 decimal places, you can use these buttons up here. So you can increase the number of decimal places or you can decrease. And so it just makes sure that your data and your graph maintains precision. All right, so now what we've done is we have, sorry, it's just changing to a pen there. We've got your data in and we want to graph it. So the next step that you're going to do is you're going to select the data that you want to graph, and then you're going to hit insert. So we are going to be inserting a graph, and we're going to be inserting a scatter chart. So you're going to click up at the top, click insert, go to chart, and then there's an arrow down so you can choose what type of chart. We're going to choose a scatter chart. And this is going to be just the dots. We don't want them to connect, even though I have very nice linear data here. We want to just put the dots and then let the, what do you call it? The computer, I guess, add a line of best fit afterwards. So we're not telling it to connect the dots. We're going to do a line of best fit afterwards. So we're going to take this chart, and then the next thing I like to do, I mean, some people like to display the data with their chart, so they'll kind of size it so that it prints and you've got your chart and your data. What I like to do is move my chart to a new page so that my chart takes up a whole thing. So I'm going to right click, I'm going to click move chart, and I'm going to click new sheet, and that's going to make my chart take up an entire new sheet. Now I'm just talking this through. If this is something that you need extra help with, I can definitely print you off steps for this. Yeah, but just let me know. Okay, so the next thing we need to have a good, I shouldn't be filming this late at night, a good graph is a chart title. So we're going to go in here. I'm just going to move some of the stuff that's in front of me. And we're going to click on chart title so that we can insert a chart title. So we're going to click here. And what should the title of this chart be? Well, the title of this chart should be the mass of water, or it didn't say what it was, of a liquid at given volumes. So you want your title to include your independent and your dependent variables, and you want to look at the like what's going on there, as well as any other detail they can give. So all I knew it was a liquid, so I wasn't sure what else to write. And if you're not sure where I got that from, it was just at the top of this note. So it says 2 chemistry students were measuring the mass of a liquid at different volumes, and then they're predicting that there's going to be a linear relationship. And look at that, it's a pretty awesome linear relationship. The next thing we need to have a good graph is that you want to have axes labels. So anytime you want to add something to your graph, if you click on it and you click the plus sign, it allows you to add things. So the next thing I'm going to add is axes titles. So for my y-axis, I'm going to label this guy, if it'll let me, let's do that. This is going to be mass in grams. So you always want to say what it is and include the units. On my x-axis, this is going to be volume in milliliters. Great. And then the next thing we're going to do is add a trend line. So I'm going to hit the plus sign again. I'm going to go down to trend line. Now, if I go to do a trend line like this, if I were to click the button, I don't know if you noticed what happened, but the graph all of a sudden went into the negative. So it's going to do the best line of fit going through whatever intercept it wants it to. But we specifically know that when the volume is 0, the mass will be 0. So instead of clicking trend line, I'm going to hit the arrow over and I'm going to hit more options. And I'm going to set the intercept to 0. That way my graph stays all in the positive and I know that it's going to be a direct linear relationship. The other thing you'll also do is display the equation on the chart. It's a really good way of checking to see if the slope that you solve for is the correct slope. All right. The next thing that we're going to do is we are going to use this line of best fit to find the slope. Now, again, I don't know where we got this data from. I did take it from somewhere. But it is amazing data. And so if you look at this, it's pretty linear. So I could actually use either of these two data points because the line goes through it perfectly. But just in case it didn't, I want to show you that sometimes when your line of best fit doesn't pass through data points perfectly, you need to find a point that you can use. And so I'm going to show you that you can add axes, or sorry, grid lines, and you're going to click on minors. And what that does is it just breaks up your scale a bit more and gives you more places that your graph might go through a perfect axis spot if you're not going through a perfect data point. You can also click more options. There's a paint can here. I find that when I print them like this, the axis lines are so faint, they're hard to see. So one thing you can do is change them. So this is the major grid line that I'm changing, but I could change it to be a bit of a darker color. Then I could go and click up here. I could click the minor in the verticals and I could make them a bit of a darker color. Then I could go to my horizontal axis and my majors and I could make them a different color or a darker color, and my minors and I could make it a darker color. And then it just makes it really nice to be able to pull data off of. So that is my completed graph. So again, take your data, insert scatter plot, make sure you have a title and an axis titles, and then make sure you add your trend line. And then I like to put my minor grid lines in there as well. So now what we're going to do is we're going to use this graph to answer the questions. So this is the graph of that data, a perfectly drawn graph. And the next thing we're going to do is calculate slope. So how are we going to do that? Well, we are going to look for somewhere that my line of best fit perfectly goes through. So if we kind of cruise in on this guy again, I can definitely use a bunch of my data points. I mean, I could use, I wonder if I can draw on here. See if it'll let me. Let's pick a color. Okay, I could use this data point that it goes through really nicely. Oh, that's weird. It's writing way up there. Okay, I can't write on here. But you could see that this bottom data point down here, it is definitely going through really nicely there. It's also going through this data point pretty perfectly, or this data point. Not so much this one up here, definitely not that one, and definitely not the top one. The other option is you pick somewhere that your axes go through. So if I look here, I'm like, it pretty nicely goes through this point here that I would call 11.0, and then over here and call that 9.0. So again, you could use this data point because your graph does definitely go through it perfectly, or you could use this junction here because your graph also, or your line of best fit also perfectly goes through there. So let's use this guy. Let's use the 11.0 and the 9.00. Okay. Can we remember that? So we're going to use the 11.0 and make sure you know which ones that is, if it's your X or your Y. I opened this in Adobe and it drives me nuts. Okay, so the point that we were going to use was 11.9. So the 11 is my X value and the 9.00 was my Y value. So then my slope would be 9.00 minus 0 all over 11.0 minus 0. Okay, 9 divided by 11 gives me a slope of, to 3 sig figs, 0.818. Now, what it's nice to do is just go back to here and double check. This one said 0.819, so we're pretty darn good. And again, I always kind of get a little bit unsure, like, should we just use this one? I mean, the calculator generated it, but it is a good skill to be able to know how slope was determined. So then either you know what it represents or just how to find it if you draw it. So my y-axis was representing, oh, that's funky. I'm not too sure what's going on there. There we go. My y-axis, it's not letting me, sorry about this. There we go. My y-axis was representing mass in grams, and my x-axis was representing volume in milliliters. All right, sorry about that. I had to open this in Edge because Adobe was just being so annoying. Okay, so when we look at this, our y value was our mass and it was measured in grams, and our x value was our volume and it was measured in milliliters. So what does my slope represent? Well, my slope is 0.818 grams per milliliter. In other words, this is the density of my liquid. Okay, all right. Then we're going to find the equation with the appropriate variables. So my equation is y equals mx, where the y value is representing my mass. So the y is mass, and so we will give it an m. And the x is representing volume. You know what I mean? And we'll give it a v. So mass is equal to 0.818 times the volume. So then the next question is, did the experiment verify their prediction? So they were predicting that there was a linear relationship, and yes, it came out as a linear relationship. So what we would say in our conclusion is there was found to be a direct linear relationship between mass and volume at a rate of 0.818 grams per milliliter. Awesome. Hopefully you're feeling more confident in how to graph and how to interpret a graph, and specifically these linear graphs. Take care.